Mastering high school math isn't just about memorizing formulas, it's about understanding where they come from. If you want to stop feeling like math is a mystery and start seeing the logic behind every exam question, you are in the right place. Today, we are counting down the top 10 most important mathematical derivations that will not only secure your diploma but change the way you think about numbers. We are going from number 10 all the way to the number 1 most essential proof. This journey will take us through geometry, trigonometry, algebra, and calculus. Each of these proofs represents a massive milestone in human thought. Understanding them means you no longer have to rely on a formula sheet, you will have the math built into your own logic. Let's dive straight in and start our countdown. Starting our countdown at number 10, the volume of a sphere. You know the formula V equals 4 over 3 times pi times r to the power of 3, but have you ever wondered why that 4 over 3 is there? Why not 5 over 3 or just pi r cubed? This formula is essential for everything from measuring planets in astrophysics to calculating the volume of a raindrop or a fuel tank. We derive this using the power of calculus, specifically the method of solids of revolution. Imagine a coordinate system. We draw a semicircle described by the function f of x equals the square root of in parentheses r to the power of 2 minus x to the power of 2. If we spin this semicircle around the x-axis, it traces out a perfect sphere. To find the volume, we use the disk method. We imagine the sphere is made of an infinite number of incredibly thin vertical slices, or disks. Each disk has a radius equal to the height of our function at that point. The area of one such disk is pi times the radius squared, which in our case is pi times the square of the square root of in parentheses r to the power of 2 minus x to the power of 2. This simplifies beautifully because the square and the square root cancel out, leaving us with pi times in parentheses r to the power of 2 minus x to the power of 2. Now, we use the integral to sum up all these disks from the far left of the sphere at negative r to the far right at positive r. The integral of r squared with respect to x is r squared times x, and the integral of x squared is 1 over 3 times x to the power of 3. When we plug in our boundaries, r and negative r, we get a fascinating result. At the upper bound, we have pi times in parentheses r to the power of 3 minus 1 over 3 r to the power of 3, which is 2 over 3 pi r cubed. When we subtract the lower bound, which is negative 2 over 3 pi r cubed, the two negatives turn into a positive. Adding them together gives us the final, elegant result of 4 over 3 pi r cubed. It is a perfect example of how calculus can solve 3D problems that seem impossible at first glance. At number 9, we have a cornerstone of trigonometry, the derivative of sine of x. The result is cosine of x. This is the foundation for understanding waves, alternating currents, and even the vibration of guitar strings. To prove this, we cannot just look at a graph, we must go back to the formal definition of a derivative, which is the limit as h approaches 0 of the difference quotient. We start with the fraction sine of in parentheses x plus h minus sine of x, all divided by h. Now, we need a way to break apart that x plus h inside the sine function. We use the trigonometric addition identity, sine of in parentheses a plus b equals sine a cosine b plus cosine a sine b. Applying this, our numerator becomes sine x cosine h plus cosine x sine h minus sine x. This looks messy, but we can reorganize it. We group the terms involving sine x together and the terms involving cosine x together. This gives us two separate limits to solve. The first part is sine x times the limit of in parentheses cosine h minus 1 over h. The second part is cosine x times the limit of sine h over h. Now, we use two fundamental geometric limits that are taught in every calculus class. The limit of sine h over h as h goes to 0 is exactly 1. This is because for very small angles, the sine of the angle is almost identical to the angle itself. The other limit, cosine h minus 1 over h, goes to 0 because the cosine of a tiny angle is almost 1, and 1 minus 1 is 0. Plugging these values back into our derivative expression, we get sine x times 0 plus cosine x times 1. The sine term vanishes completely, leaving us with the clean result, the derivative of sine is cosine. This simple relationship is why sine and cosine are the language of everything that rotates or oscillates. Moving to number 8 on our list, the cosine rule. This formula, c to the power of 2 equals a to the power of 2 plus b to the power of 2 minus 2 a b cosine c, is like the Pythagorean theorem but with a correction factor for any triangle. It is a masterpiece of combining algebra and geometry used in navigation, 3D modeling, and even GPS technology. To derive this, we place a general triangle on a coordinate grid. We place vertex C exactly at the origin, which is 0, 0. We let side B lie along the x-axis, which means vertex A is at the coordinate b, 0. Now, where is vertex B? Using the definitions of sine and cosine in a right triangle, we can describe the coordinates of vertex B as a times cosine of angle C and a times sine of angle C. Now that we have the coordinates for all three corners, we can find the length of side C using the distance formula. Side C is the distance between vertex A at b, 0 and vertex B at a cosine C, a sine C. We square the differences of the x-coordinates and the y-coordinates. This gives us in parentheses a cosine C minus b squared plus in parentheses a sine C minus 0 squared. When we expand the first part, we get a to the power of 2 times cosine squared C minus 2 a b cosine C plus b to the power of 2. The second part is just a to the power of 2 times sine squared C. Now, we look for common terms. We have an a squared cosine squared and an a squared sine squared. If we factor out a squared, we are left with in parentheses sine squared C plus cosine squared C. As every student knows, this identity equals 1. Therefore, those two terms simply become a squared. Adding back the other parts of our expansion, we arrive at the full formula, a squared plus b squared minus 2ab cosine C. It shows that the Pythagorean theorem is just a special case where angle C is 90 degrees and the cosine term becomes 0. At number 7, we have the sine rule. This tells us that a over sine of a equals b over sine of b. This is crucial for solving triangles where you don't have a right angle, which is most real-world situations in surveying or architecture. To derive it, we take a general triangle and drop a perpendicular line from one vertex down to the opposite side. Let's call this line the height, or h. This single line splits our general triangle into two right-angled triangles. Now we can use basic trigonometry. In the first right triangle on the left, the sine of angle A is the opposite side h divided by the hypotenuse b. If we rearrange this, we find that h equals b times sine of A. Now let's look at the second right triangle on the right. The sine of angle B is the opposite side h divided by the hypotenuse A. Rearranging this gives us h equals a times sine of B. Now, here is the clever part, since h is the same line in both triangles, it must have the same length. Therefore, b times sine of A must be equal to a times sine of B. If we divide both sides by sine A, and then divide both sides by sine B, we get the elegant ratio, a over sine A equals b over sine B. We can repeat this exact same process by dropping a height from a different vertex to include side C and angle C. This proves that the ratio of any side to the sine of its opposite angle is constant for the entire triangle. If you are finding this countdown helpful for your exam prep so far, make sure to like this video and subscribe to the channel. It really helps us create more deep dive content for your studies. Now for number 6, the area of a circle, a equals pi times r to the power of 2. This derivation is incredibly visual and dates back to the ancient Greeks like Archimedes. It's one of the earliest examples of what we now call integral calculus. Imagine a circle with radius r. Now, imagine cutting this circle into many tiny, equal pi-shaped slices, or sectors. The more slices you make, the better. If you take these slices and arrange them in a row, pointing them alternately up and down, they begin to form a shape that looks remarkably like a rectangle. As the number of slices becomes infinite, the jagged top and bottom edges become perfectly straight lines. The height of this newly formed rectangle is simply the radius of the original circle, r. But what about the width? The total length of the crust of all our slices combined is the circumference of the circle, which is 2 times pi times r. Since we put half of the slices pointing up and half pointing down, the top edge of our rectangle is half of the circumference, and the bottom edge is the other half. Therefore, the width of our rectangle is pi times r. To find the area of this rectangle, we simply multiply the base by the height. Pi times r multiplied by r gives us pi times r to the power of 2. This is a brilliant way to see how a curved shape can be transformed into a linear one to find its size. Coming in at number 5, the equation of a circle. It is written as in parentheses x minus h squared plus in parentheses y minus k squared equals r to the power of 2. This formula describes every point at distance r from a center point h, k. The derivation is actually just the Pythagorean theorem in disguise, and understanding this makes coordinate geometry much less intimidating. Imagine a circle on a graph. The center is at the point h, k. Now pick any random point on the circle's edge and call it x, y. By the very definition of a circle, the distance between these 2 points must be the radius r. If we draw a horizontal line from the center to the x position of our point, and then a vertical line up to the y position, we have created a right-angled triangle. The length of the horizontal leg is the difference between the x values, which is x minus h. The length of the vertical leg is the difference between the y values, which is y minus k. The hypotenuse of this triangle is the radius r. Now, we apply the Pythagorean theorem. The square of one leg plus the square of the other leg equals the square of the hypotenuse. This gives us in parentheses x minus h squared plus in parentheses y minus k squared equals r squared. If the circle is centered at the origin, 0, 0, the formula simplifies even further to x squared plus y squared equals r squared. It is a perfect bridge between the world of shapes and the world of algebra. At number 4, we have the sum of an arithmetic series. When you need to add up a long list of numbers with a constant difference, like 5 plus 10 plus 15 and so on, you use s sub n equals n over 2 times in parentheses a sub 1 plus a sub n. The derivation of this formula is a classic story in math history. Legend has it that the young mathematician Carl Gauss was asked to add all numbers from 1 to 100. He did it in seconds. He realized that if you write the sum forwards and then write the exact same sum again backwards underneath it, something amazing happens. Let's call the first term a sub 1 and the last term a sub n. When you add the first term of the top row to the last term of the bottom row, you get a sub 1 plus a sub n. When you add the second term of the top row to the second to last term of the bottom row, you also get a sub 1 plus a sub n. In fact, every vertical pair in these 2 rows sums up to the same value. Since there are n numbers in the series, you have n of these pairs. So, the total of both rows combined is n times in parentheses a sub 1 plus a sub n. However, since we only want the sum of one row, we must divide this total by 2. This gives us the final formula, n over 2 times the sum of the first and last terms. It's an incredibly efficient way to handle large datasets or financial calculations involving interest over time. We are entering the top 3. These are the heavy hitters of high school mathematics. If you want more tips and deep dives to help you ace your math diploma, hit that like button and subscribe now. Your support keeps these lessons free and accessible for everyone. Number 3 is the legendary Pythagorean theorem, a to the power of 2 plus b to the power of 2 equals c to the power of 2. This is the heart of Euclidean geometry. While there are hundreds of ways to prove it, one of the most elegant is the rearrangement proof using area. Imagine a large square with a side length of a plus b. Inside this square, we can place 4 identical right-angled triangles, each with legs a and b and hypotenuse c. We can arrange them so that they form a smaller, tilted square in the middle. The side of this inner square is the hypotenuse c, so its area is c to the power of 2. The total area of the large square can be calculated in 2 ways. First, as the side length squared, which is in parentheses a plus b squared. Expanding this gives us a to the power of 2 plus 2ab plus b to the power of 2. Second, we can calculate the area as the sum of its parts, the 4 triangles plus the inner square. The area of one triangle is 1 over 2 times a times b, so 4 of them make 2ab. Adding the inner square, the total area is 2ab plus c to the power of 2. Now, we set these 2 expressions for the same total area equal to each other. On both sides of the equation, we have a 2ab. When we subtract it from both sides, it disappears completely, leaving us with the most famous equation in math, a to the power of 2 plus b to the power of 2 equals c to the power of 2. It is simple, powerful, and universal. At number 2, we have the power rule from calculus. If you have a function f of x equals x to the power of n, the derivative is n times x to the power of n minus 1. This is the ultimate tool for finding slopes, optimizing business profits, and calculating acceleration. To prove this, we go back to the formal limit definition of a derivative. We look at the fraction f of x plus h minus f of x all over h as h goes to 0. Substituting our function, we get in parentheses x plus h to the power of n minus x to the power of n. To expand that first part, we use the binomial theorem. The expansion starts with x to the power of n, then the next term is n times x to the power of n minus 1 times h, and then further terms involving h squared, h cubed, and so on. When we subtract the original x to the power of n from this expansion, the first term cancels out. Now, every single term remaining in the numerator has at least one h in it. When we divide the whole thing by the h in the denominator, the h in the second term disappears, leaving just n times x to the power of n minus 1. All the other terms still have an h, or an h squared, or even higher powers of h. Now comes the final step, we take the limit as h goes to 0. Every term that still contains an h becomes 0 and vanishes. The only term that survives is the one without an h, n times x to the power of n minus 1. This derivation is the gatekeeper to all of higher analysis and physics. And finally, the number one most important derivation for your diploma, the quadratic formula. It is the king of algebra, used to solve any equation in the form a x to the power of 2 plus bx plus c equals 0. Most students just memorize it, but the derivation, known as completing the square, is where the real magic happens. We start with the standard form. First, we divide every single term by a to make the leading coefficient 1. This gives us x squared plus b over a times x plus c over a equals 0. Next, we move the constant term, c over a, to the right side of the equation. Now, we need to turn the left side into a perfect square. We take the coefficient of x, which is b over a, divide it by 2, and square it. This gives us in parentheses b over 2a squared. We add this value to both sides of the equation to keep it balanced. Now, the left side can be factored perfectly into in parentheses x plus b over 2a squared. On the right side, we combine the fractions by finding a common denominator, which is 4 times a to the power of 2. This results in the numerator b to the power of 2 minus 4ac. To solve for x, we take the square root of both sides. This introduces the plus or minus sign. The square root of the denominator 4a squared is just 2a. Finally, we isolate x by moving the b over 2a term to the other side. Since both fractions now have the same denominator, we can combine them into one final, world-famous expression x equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. This formula is the culmination of centuries of algebraic thought and is your best friend in any math exam. Understanding these 10 derivations means you no longer have to fear the why in math. You now have the tools to build these formulas yourself from the ground up. If you found this journey through the top 10 derivations valuable, don't forget to like, subscribe, and share this with a fellow student. Good luck with your diploma, and I will see you in the next deep dive.